Welcome to Wireless Future. I'm Emil Björnsson, and as always, I'm here with Eric Larsson. How are you today?
Good, Emil. How are you?
I'm good. It is warm inside and cold outside here in Sweden
it's really,
right now.
Really cold outside, in fact, at the start of the new year.
So it's a good opportunity to sit out inside and talk about something like new papers.
New papers.
So I think you found an interesting paper that has appeared recently called 6G Take Shape by Jeffrey Andrews and his colleagues Humphrey and G, and it's going to be appearing in the IEEE Bits. And they are making the point that the contours of 6G is starting to take shape. Since there's been a lot of research, but now the key technology components and driving requirements is finally something that one can not only speculate about, but having a good sense about what will actually happen. So, we have both read it. So what should we do with it? Should we discuss it?
Yeah, what should we do with it? So it came out, I think you said, in the Bits magazine, or at least the version I got my hands on is a preprint dated November 27th from last year. We both read it. Do you want to start off, Emil?
Yes, I think they start off the discussion with saying that there has been some disappointment with 5G and that this is something that they want us to learn about when designing 6G. So what is your take on 5G and the disappointment? Is it not living up to what it was meant to do?
Oh, so my take on 5G and disappointment, I think, well, every generation of systems probably comes with its disappointments. And for 5G, was it a disappointment? I don't really know. I think you know better, Emil, and we'll see what the authors of the papers also think here. But I would argue, though, that from a technology perspective, honestly, I don't know. I mean, what we do know is that some version of massive MIMO at the physical layer is implemented in time division duplexing based upon reciprocity-based beamforming with CSI from uplink pilots. Now, to what extent that really represents what we know as the textbook version of massive MIMO, I honestly don't know. And I don't know how much of this is like widely known or proprietary. But what type of processing really goes in there, I'm not sure. What seems to be the case is that the lack of coordination among cells is an issue. So that non-stationarity and unpredictability of the interference situation is a big problem. Because if you think back of textbook massive MIMO, it was all built upon a stationary situation where signal to interference ratio remained essentially constant over time, which implies no on and off random scheduling or switching of data in neighboring cells. My understanding is that that's not the case in current systems. On the contrary, current systems are subject to a lot of flashlight interference that goes on and off in neighboring cells, and which is totally uncoordinated with what's going on in the home cell. And this concerns both allocation of pilots and the data transmission itself, which of course totally changes the game. So in that respect, I'm slightly disappointed. I mean, to start with, there is no reason for all this on and off switching of or scheduling of data. Most data could be circuit switched advantageously to create a stationary and predictable interference environment, which is not being done in 5G to my understanding. So if you ask me, I'd say that's the short answer. Because of this, we probably failed to realize the full potential of what massive MIMO with reciprocity-based beamforming has to offer. That's a technology perspective, and it's mostly limited to the physical layer. I mean, what I said now also concerns the higher layers, because the reason that we have all this unpredictable and flashlight interference is that high layer protocols are not well designed. But it's mostly a physical layer technology perspective.
Right.
What is your perspective, Emil?
Yeah, I think based on what you're saying with the physical layer there, that yes, since it's packet based and we have a lot of traffic that is just small packages, then when you have this huge capacity in the network, you don't really see the benefits of MIMO so very often in how it was implemented, because every time there is a packet to transmit, or there are many packets, they don't fill up the entire frequency domain, so it's easier to just put users on different subcarriers instead of scheduling them on the same subcarrier using MIMO to get a higher data rate, just because the network has too high capacity. Then what... if the technology really is disappointing in terms of what capacity it can deliver, I think it's a bit too early to tell, because if you build a new technology that can deliver a lot of extra data, then you need to create that data traffic before you can actually see if the network were capable of delivering that much traffic or not. Of course, you can make some test where you just put a lot of people on the field and they all should stream data all the time and make those tests, and then it seems to work reasonably well. But I think it's a bit too early to tell if we can actually deliver 10 times more or 20 times more data in 5G networks compared to 4G.
Mm. Yeah, I think, and again, to really test that, you would need high-layer protocols that don't create small packets of data that is naturally circuit switched, and they could be transmitted in a way that creates a more or less totally stationary and predictable interference situation. But now I think we are going off a tangent a bit here into very specific aspects of MIMO. Shall we stay on the disappointment track?
Yeah, when it comes to disappointment, I think the other aspect of this is that when they were advertising 5G, they were not talking about MIMO or anything like that. In general, they were talking about, now we can have autonomous vehicles that can be wirelessly connected, or we can do remote surgery, and we can have massive amounts of Internet of Things device that can be connected. And there were a lot of these kind of use cases of technology that were advertised, and we don't have any of them right now. And I think that has built up this disappointment. And I think this is to some extent just a bad marketing strategy, because I think many of those use cases were just something that some researchers were brainstorming about when they had to come up with some technical requirements for 5G. And now we have a technology that can satisfy those technical requirements, hopefully. But it doesn't mean that the use cases will be there automatically, because there were no vendors or stakeholders who wanted to build those use cases immediately. But there are, of course, people trying to now figure out how to use 5G to make their factories more efficient, or to how to automate society and digitalize things more efficiently. So that might happen, but it's too early to tell.
Mm. So you're basically saying that much of the disappointment is that the demand is not there for these services yet.
Right, and those services might not be the actual services we will see eventually in 5G anyway. So it was a bit that when people are making preparatory work to figure out what might happen in the distant future and what would be required, then you take those things that was never really grounded in demand from customers, and you advertise them heavily towards the public, then that hits back on you later on when no one really had the intention of releasing those services. But yeah, there is a lot of work being done now on figuring out how 5G can be useful in private networks, in factories and mines and other situations. So hopefully there will be some new services as well eventually.
Yeah, probably they will. But now returning to the paper here, the authors also talk about millimeter wave specifically being a disappointment in 5G. My understanding is that millimeter wave was actually deployed in some countries, but it wasn't used, so it's more or less dismantled.
Right. So that is particularly what happened in South Korea, that they dismantled it. In US, it was deployed because the operator who deployed it didn't have any other spectrum for 5G, but then when it got their hands on lower frequencies, then they started to deploy 5G there instead. But I think also there it comes back to that It might be that millimeter wave will never really be used because the propagation conditions are too bad, but it could also be that once we have so much traffic in the networks that we fill up the lower or mid-band where we are using 5G today, when those are filled with traffic, we will need millimeter wave at some places, and then millimeter wave will come back. It was just the wrong order of deploying things that happened as well, potentially.
So you're saying the spectrum uses like water filling. You start by filling up the lower frequency bands, and then when they are full, then we can talk millimeter wave, and maybe eventually terahertz. Right. Yeah, that makes sense, I think.
In the paper, then, what do they think 6G should do differently compared to 5G?
So I think the main point by the authors here is that data rates. They will be getting like 10 times more traffic from new applications. Again, that of course remains to be seen whether they materialize or not. But there's this notion of making the network into a computing infrastructure, which I totally also share, and to support on-device AI applications, and to support extended reality, virtual reality, augmented reality, and to support like massive sensors that need to send and process data. So rather than voice and video and social media being the driving factors, it would rather be these new emerging XR, AR, VR, AI on the device, and massive sensing that would drive the traffic.
Right. Yeah. That seems to make sense. That on the one hand, we have a growth in traffic, so we need to have more capacity for that, and then the use case you're describing seems to be some of the timely ones. Maybe they are actually closer to getting used in large scale in practice than some of the ones that were envisioned in the 5G era.
Yeah, I would probably think so, but this of course remains to be seen. So with that, I would agree with the assessment of the authors.
Yeah, no, and I think to actually bring these things to life, it's always important to figure out how to monetize things like this as well, because people have their subscription for a mobile phone, for example, and if you want to charge them extra for doing this offloading of AI or computations, then you need to find a way of doing that. But yeah, it seems like people are paying a lot for ChatGPT right now for the professional versions of it, so there seems to be demand. So
that's what it seems like. I mean, so are you using ChatGPT, Emil?
Not the paid version, but no. It is a useful thing also for professor, I think, to just help out with brainstorming to see, did you figure everything out yourself or did you miss some points?
Yeah, I mean, it can do a lot of simple tasks for you. Like for example, you can input the title of a paper and ask it to give you a bibtex item, that sort of things I've used it for. Sometimes it works, but not always. It worked like 5 times in a row, and then the 6th time I tried it, I input the title of the paper, and it just spit out like strange characters in a row. So it's some glitch somewhere in this network. Who knows? Yeah.
Right. So going back once again to the paper, then the next thing they are talking about is a bit about spectrum, and we covered the upper midband in the previous episodes. Yeah. So let's instead discuss terahertz.
Terahertz. Yeah.
What about them in 6G?
Yeah, I think so. The author's view here is that terahertz will not play a major role in 6G. I would probably agree with that assessment. I think given that we hardly fill the lower bands to start with, and given that millimeter wave did not really succeed for 5G, and it doesn't seem to be a demand, the question is, for what would we use terahertz, right? And then there's also the problem with terahertz that the physics is against the problem because of, well, not really path loss, but rather the effective area of a dipole antenna shrinks as lambda squared. So you need a lot of antennas to maintain the aperture required to keep the link budget. So that's the number one. And the number two obvious thing is Doppler with mobility. And these just make everything more difficult. Anything that has to do with anything where you need to maintain an SNR for the link budget, and any situation where you want to steer a beam or use transmitter channel state information. So it's not clear to me what would be the use cases really for terahertz. The authors here also state that the main innovation needed for terahertz is largely in the circuits and hardware domain, which I, to a large extent, also would agree with. I don't think this is completely the full picture, because once you start to really look more deeply into the details, you'll discover that there are new scientific problems that emerge. For example, we had been working, I don't think we discussed this on the podcast, we probably did at some point in the past, but we're engaged in a project where we look at terahertz over plastic fiber. And then the problem is that these fibers, they attenuate the signals. Every meter or so you need a booster amplifier, and this amplifier is non-linear. So suddenly we have a system with a linear time invariant system, which is the radio stripes, in cascade with a non-linear device, the amplifier, in cascade with another piece of stripe, in cascade with another non-linear amplifier, and so on. And suddenly this opens like a lot of new scientific problems that nobody seems to have considered in the past. So I think it's completely true. I think it's 90% true that most of the development required here is in the circuits domain.
Right, but I guess channel modeling and MIMO and these type of things is something that also appears there. But I think when they make these kind of statements, I think that they are referring to the access between the user devices and the network. Then we also have the backhaul between different base stations, for example.
Absolutely.
And they have traditionally been operating at millimeter wave frequencies. And if we then move the access a bit upwards along the frequency in order to get more capacity, then we might do something similar with the backhaul links. And probably there we will move closer to the terahertz frequency more rapidly because, you need more data traffic or higher capacity on the backhaul link when you have accumulated all the traffic within your cell and need to pass it on somewhere else if you don't have a fiber.
Yeah, absolutely. The question is also what is 6G, right? I mean, I tend to think of 6G as mobile access, but now if we include also fixed, or at least if we include like backhauling, then certainly that's already being done at millimeter wave, and probably in the future we'll use even higher bands.
Right. And potentially you don't need to standardize how those backhaul links operate, so then you have more freedom to choose your frequencies. What about the reconfigurable intelligent surfaces then?
Yeah, reconfigurable intelligent surface. RIS or IRS? I think the community seems to have agreed on RIS to be the name.
Right.
So I mean, I would concur with the authors here. It's an interesting development from a technical point of view, but it's very difficult to see where the deployment or the use cases would be in 6G. And I think the main problems with RIS is, number one is deployment, because you need a lot of space. The whole idea is that you need a large planar area to put them. And number two is that you need control logic and control signaling to reconfigure all these small reflecting atoms or scattering atoms in real time. And the number three thing, which is really the real elephant in the room, I think, which is hardly being talked about anywhere, is that they lack band selectivity, substantially lack band selectivity. I mean, you can get some band selectivity, but not nearly enough to be useful. And of course we've known this all along, and it's also clear now that the RIS was discontinued in the 3GPP standardization. So they are unlikely, I think, to play any major role. Possibly in niche cases. I can't really think of any. I mean, the case I can think of is if you want to build probably at high carrier frequencies, you want to build a beamforming transmitter. As an alternative to building a phased array or with a Butler matrix or with phase shifters, you might build a single antenna that sits in the near field of a reflect array. That's not really RIS, at least it's not RIS the way it was envisioned for enhancement of cellular communications. I think on that one, that would be my view aligned with the authors here. What do you think, Emil?
Yeah, I was positively surprised how quickly the RAS technology actually became something that was field trialed. I mean, people started building it in their labs and they tried it out there, and then there were experiments happening. And I think last year there were 2 IEEE ComSoc Best Paper Awards given to some of those early experimental works. So that was a positive surprise that one can actually build them. But I fully agree with you that it's hard to find these really good use cases where all of the complexities are figuring out how should we rent spaces for these areas, how should we operate them, how do we deal with this non-band selectivity where one operator would change the band or propagation conditions for another operator. All of those things seems to be complicated. And then if you run simulations on this as well, it seems like you can see massive performance gains if you ignore that there are also propagation paths directly between transmitter and receiver, maybe going straight for a building or being scattered and so on. And for reasonably sized RS, you might be giving some performance gains, but they are not enormously big in more real propagation environments.
No, I mean, it's a cool technology, and no doubt you can write a lot of cool papers and cool experiments in the lab. But from a deployment perspective, this simply doesn't seem to be useful. I don't know about indoors. I mean, you can possibly make the case that indoors you don't have the issue with band selectivity to the same extent. And you might not have a space issue if you own the building. I mean, rather than putting like paintings or something, you put a wreath there. Once a wreath there, could have a painting. But then I think it really stands to reason, would you not rather put just deploy an additional small access point or a small relay or a repeater there? I mean, which does the same job but is much smaller and simpler and presumably cheaper. So it's really hard to say and or to envision, I think. And
it really goes down into scenarios where you want to actively engineer your propagation environment. And I think we have seldom done that. Of course, telecom operators are trying out different deployment locations and see what coverage they are providing, but actually going into the details on saying here is a small region where we will get very bad coverage, let's put up an RS in order to redirect signals into there. You could do that, of course, but we are not used to doing it. Maybe it's easier in the building, as you're saying.
Yeah, and on top of that, I mean, I think a much more viable and simpler solution would be to put a small network-controlled repeater there, which we could maybe return to at some other point in time. So the authors also state here that it's not clear the benefit versus cost of deploying a REIS compared to deploying a full-fledged 6G small cell. I would somewhat take issue with that, though, because deploying a small cell usually doesn't really solve the problem. It just creates more interference unless it's coordinated phase coherently with surrounding whatever access points or cells. And then that's not small cells anymore. Then it's more a version of distributed MIMO or cell-free massive MIMO. And this seems to be one of the long-lasting misconceptions in the wireless community, that ultra-densification with small cells could ultimately solve the capacity problem and create uniform coverage, which is not the case, as we know, and as we've known for a long time. Every single serious comparison that I know of between small cells and cell-free massive MIMO show orders of magnitude in difference in performance when you look at lower percentiles. I mean, if the goal is really to enable or to provide uniform quality of service, then small cells are completely useless. And the only viable solution is some form of coordinated MIMO, be it cell-free massive MIMO or distributed MIMO, which is essentially the same thing. But you need phase-coherent coordination so that you can do joint beamforming from geographically separated access points. So that one I would disagree with. No, small cells will not solve the problem. They are certainly a better solution than deploying REIS. There's no question. But they will not solve the problem. What do you think, Emil?
I think that the selling point of the REIS compared to the small cell is that the small cell will require like a fiber backhaul and power connector. The REIS will only require power connectors you can deploy to specific locations. If you could somehow make it so that it is harvesting the energy for its operation from other places, you don't even need a power connector, and then you can deploy it in new places. So there are these kind of potentials, but it also seems to come with a lot of drawbacks as well. So it doesn't.
That one I could maybe buy, but I think you need to compare apples to apples here, right? So you're right in that if you don't have backhaul or even the possibility of installing backhaul, then you can't put a small cell, full stop. Or you could do backhaul over wireless, perhaps. But let's say that would be suppose that's unviable. I mean, so then you couldn't deploy a small cell. So the comparison then would be Reese against something else. And then the question is, what is that something else? And so I think then the relevant case is, would you deploy a Reese or would you deploy a small network controlled repeater? That's a real question there, which we, again, maybe will return to, yes.
Yeah, but there's one form of Reese that I find particularly peculiar when it comes to the deployment, and this is known as star Reese. So this is a surface that is not only reflecting signals on one side, but it can also control how the signals goes through it. And that will mean that you somehow need to have open air on both sides of it. So in an indoor scenario, you can essentially make a hole in the wall and put up a Reese there. And then you could wonder, but why not keep that hole then?
Or why not install a waveguide? I mean, there are solutions to provide coverage through walls by means of waveguides. Essentially, you drill a hole through the wall and then you put like an antenna on either side. So this also becomes a bit of semantics and a question of terminology. What does a Reese mean? What does a repeater mean? What does a waveguide? I mean, waveguide is clear what it means, I think. But when does something active become, or passive become active versus like, anyways, maybe.
Yeah, and if you make a hole if you make this hole in the wall, what happens with the acoustics and heat isolations and everything? Yeah, so it seems like
with the heat isolation when you got like minus 10 centigrades outside.
Yeah, so it should probably be through inner walls. All right, let's move on and talk about waveforms. Will we get any new waveforms in 6G?
So I think the authors of the paper essentially say no. Quoting from the paper, in summary, OFDM and OFDMA appear to be unbeatable in several different dimensions. Near optimality from COM theoretic standpoint, flexibility and adaptability for different use cases, mature and efficient implementations. That aligns with my view totally as well. And in fact, I think every more or less communication theorist would agree that if you just start with a blank paper and want to carve out like what is the most natural and simplest way of dealing with a dispersive channel, you would conclude OFDM. In fact, I think that the entire CDMA journey was a complete detour. We could have built OFDM from the beginning. The authors also did talk briefly about other waveforms that could be built. In fact, on top of OFDM, there's this OTFS that I believe we talked about in the podcast maybe a year ago or so. Now, OTFS could be viewed more or less as an add-on on top of OFDM. And there might be situations where that's useful, like if you have a lot of sparsity in the delay Doppler domain and a lot of fast time variations, but it doesn't fundamentally really change anything. So the virtue of OFDM is that, number one, you convert a dispersive channel into parallel frequency flat channels, and that just simplifies so many other processing tasks. In particular, it simplifies and integrates so naturally with MIMO and multi-user MIMO. And it also permits easy multiplexing of users in the frequency domain. What do you think, Emil? Is there a need for any new waveforms?
I don't think there is any big need for that. Of course, when we talk about OFDM, we normally refer to the cyclic prefix version of it, where you pay a price in terms of that you spend a few percentage of your resources on creating the cyclic prefix. But if you use some other waveform, there will be a price to pay somewhere anyway for how to make this waveform actually work and they coexist with surrounding
that's
things.
true. If you have very long dispersion, then the cyclic prefix has to be correspondingly that long, and you would waste a little bit. Now, you should also keep in mind that there are methods to reduce the waste associated with the cyclic prefix to actually harness the samples that are received during the prefix. And there are also other types of prefix than cyclic that can be used. But let's not go there maybe right now. So the one drawback of OFDM would be the peak to average ratio. And that one can be a serious complication in some applications. The author here say that even some satellite systems where you would think, that you're extremely power constrained and peak to average would be a big deal, but they still use OFDM. I could think that there might be applications where you operate at fairly low spectral efficiencies and you're extremely concerned about energy efficiency, and then maybe OFDM would not be really the completely the way to go. One thing that the paper doesn't mention, but which I think still has a role to play, is constant envelope or continuous phase modulation for cases where, this is somehow it's difficult to combine with multi-user MIMO, but it might be cases where we don't care about spatial multiplexing, we don't care so much about spectral efficiency, or rather we can't anyway get a very high spectral efficiency, but we care a lot about robustness to nonlinearities in the hardware, and then continuous phase modulation would be unbeatable. Constant envelope in general, and particularly constant envelope where you keep the phase continuous. But again, that's probably would be for niche applications. That would not be the applications that would offer the large data rates they were talking about for 6G here.
Right. And there are these narrowband IoT solutions, or whatever they're called now in 5G, where you are taking some parts of your frequency resources and you transmit in a slightly different way there for IoT devices. And in principle, you could probably do something similar for high mobility users and operate your system differently on some of the subcarriers just to cater for those ones. But I think it becomes dangerous if we try to reconfigure the entire waveform just to cater for a few users that appears occasionally.
Yeah, I would probably concur with that.
So then we have our waveform, and inside of it we put data, and that data needs to be encoded, and so we can protect against errors. So what about the channel coding? Will it change?
Code. Yeah, no. So the author review here is that channel coding is essentially done. That we would continue to use LDPC and polar codes, LDPC for long blocks and polar codes for shorter blocks. That seems plausible. I'm sure there are still gains that could be harnessed by further optimizing different hardware implementations and tweaking these codes to permit a more efficient implementation. But the bottom line is that these codes are already so good, and particularly the PC codes for longer blocks. This has been known for many years now. I think it's 25 years ago almost. Richardson and Banke optimized the degree distributions for LDPC codes. I still remember when I saw this for the first time for the AWGN channel, and you got 100,000 bits, you get 0.1 or something, or was it a million bits maybe? You get 0.1 dB from capacity on the AWGN channel, and the error probability just goes straight line, like a straight line down, like a waterfall straight line like this. And of course you get an error floor that you need to handle through some outer code that deals with that. But these are so extremely optimized and efficient that really I don't think there's anything left to gain there. Perhaps in the short block length regime, but again, even though a lot of packets are short, but the vast majority of bits sit in long packets. So one thing that the authors mention, and which is a bit interesting, that's now seems like it's popping up again. It was also popular 25 years ago to look at constellation shaping. When you have higher order constellations, then you can gain a little bit by assigning non-uniform probabilities to the different constellation points to make the overall distribution of the signal look more like a Gaussian bell shape. And there's a mention here of a 1 dB figure. My recollection is that for large constellations, the gain you can get if you compare a uniform QAM to a Gaussian is on that order. So there could be like a dB or something to squeeze out on the link budget here, which might be significant in some applications. The price to pay, of course, is complexity, because then you need other types of encoders and demappers to deal with these non-uniform probabilities. My gut feeling is that problem could be solved if we throw enough, let's say, innovation and talent and resources at solving it algorithmically. So for large constellations, I mean, I've heard, if you got like QPSK, obviously there's nothing to gain. If you got 16 QAM, there might be a little bit to gain. But if you go up like 1024 QAM or something, so you got a really good link budget and no interference, then yeah, sure enough, you could gain maybe not the dB fully, but at least a little bit. So that one I think is interesting as a further optimization of the digital transmission physical layer.
Right.
And it also goes well with MIMO. And here I don't agree. I think I disagree with the authors. They say that for MIMO, the demapping may be too complex for 6G. But the whole point, of course, is that with massive MIMO, we essentially separate the multi-user MIMO channel into parallel scalar channels. And then you can use whatever favorite modulation encoding scheme on top of that, including constellation shaping. So that I would say should not be an issue.
Right. No, I totally agree that from the encoding perspective, we have a long history of developing powerful codes, and we have gradually been using them also in the cellular standards, and with 5G, with LPC and polar codes, they are working really well also for short block length. I think one of the concerns that people have been talking about is the decoder implementation of things. Maybe not because of the multi-user MIMO aspect that you were describing, but because if you are transmitting a large amount of data and you need to decode it rapidly, then the power consumption of the receiver will grow linearly with the amount of data, or maybe faster than that if you are using a lot of layers and a lot of higher order modulation schemes.
Yeah, that's an interesting point. I mean, so I maintain that current implementations are extremely efficient, but you're right that the question is how this scales, right? So if you double the data rate, would the energy or the power consumption or the energy consumption per bit, then would that remain the same, or would it increase, and how fast would it increase? Because now we're discussing like 10 times higher rates or maybe 100 times higher rates. So you don't want 100 times higher. No, fair enough.
But I think there are projects that have been demonstrating how you can even reach terabit per second decoders with relatively, milliwatt measured power consumption decoders as well.
Too. I mean, milliwatt is nothing here. So.
Yeah, so it is hopefully not a showstopper or anything like that, but such things will of course have to be integrated into the hardware accelerated receivers as well.
Definitely into hardware accelerated receivers. I mean, I think all of these techniques will be built upon dedicated circuits that to do the job.
So you touched upon MIMO before. Will there be anything new in the MIMO world, or it will just be the same but maybe more antennas?
Yeah, so the question is what would new mean in the MIMO world? So I think the general, the view put forth by the authors here is that 6G physical layer would be native in MIMO, which makes total sense to me. I understand there might be political reasons to keep FDD operation in some bands and so on. But again, if you just start from a clean sheet to design a MIMO scheme, you would rather quickly arrive at the conclusion that you would operate in TDD and you would use reciprocity for CSI. which is what most people call massive MIMO, which oddly enough is the term seems not to be used in the paper here, but I mean, which is of course the backbone of how MIMO works in the 5G standard in TDD, and would continue to do so in 6G. All reasonable means. There's also mention here on holographic MIMO, referring to ultra-dense arrays or even continuously radiating surfaces. Well, I don't know if I ever understood what holographic MIMO really means, but if
right.
What is meant is like a large I think you know better, Emil.
I think when people introduced that term, the idea was that what if you have a surface consisting of very, very many small antennas that are closer than half a wavelength apart from each other, then eventually it will be more like a continuous surface where you can control everything compared to having some discrete antenna locations. But this is more
sure, but I mean, haven't we known all along that there is no benefit in having antennas more closely separated than half a wavelength? So to me, this is just a gimmick. I mean, basic point is that building a larger array totally makes sense. You would build that array from small, probably patch antennas that sit half a wavelength or approximately half a wavelength, or no closer than half a wavelength, I would argue, together. And to me, this is just massive MIMO in an evolved form, but it is the same thing.
Right. Yeah. If there are some power gains to be obtained by this, or some superdirectivity gains in certain scenarios, and so, then it seems like something that will not be utilized in 6G anyway, because it will be niche.
No. I mean, those are really totally niche cases that would, there's also mention here that for low mobility, dense urban scenarios, we will see incremental progress towards forms of cell-free MIMO with multi-base station connectivity for increased area spectral efficiency. So I think cell-free massive MIMO and distributed MIMO, D-MIMO, obviously the same thing. And I totally agree. I mean, I think D-MIMO is the ultimate form of building MIMO. And the key point here, the key difficulty in building D-MIMO, of course, backhaul is there, right? It's an issue. But the key difficulty is to synchronize the phase for joint coherent beamforming on downlink, which is, to me, a totally under-researched problem that we really should throw more talent at. If one can afford a central clock and distributing that clock signal to the access points, the problem would essentially go away. But I think more realistically, the MIMO deployments, you would be requiring periodic realignment of the phase in between the access points, and this is the deal breaker to make the MIMO work. I mean, we tend to talk a lot about channel state information, measuring the channel, which of course on uplink, data and channels, pilots and the data see the same channels, it's easy. On downlink, we can rely on reciprocity, but for reciprocity to work, the panels have to be aligned in phase. And this is like the elephant in the room that's almost not talked about anywhere in the MIMO literature, and not mentioned in the paper here either, for that matter. So this is the real problem in building D-MIMO or cell-free MIMO.
Yeah, so this is certainly the real technical challenge. Then with synchronizing the antennas, then there is of course the business challenge that people are might not be willing to pay more for getting better coverage or more consistent performance, even if they really want to have it. So yeah,
that's another one. Will it be worth it? I mean, will you be willing to pay so much more to improve coverage from whatever 95 to 99 or 99 to 99.9 or whatever percentage? Nobody knows. I think this again way back. It is where we started the discussion on applications that will drive the development. But in terms of new MIMO solutions, I would say the ultimate embodiment of MIMO is really distributed MIMO, and it comes with its challenges of providing backhaul and aligning the phase.
So what about machine learning or neural networks or AI or whatever we call it, and the physical layer? Do we really need to standardize MIMO and the channel codes and all these kind of things, or can we just learn these things on the fly?
Yeah, it's a good question. No, there's no need to standardize anything. You just throw out hardware and then you hit the button and we just automatically train itself, and it will learn MIMO, it will learn multiplexing, and learn everything that's in your books, Emil, about, cell-free and zero forcing and all these things, right? Just kidding. I think the author's view here is that the 5G physical layer will not be wholesale or even significantly replaced in 6G by neural networks. I would tend to agree with that. The main reason being that the main computation-intensive tasks that are required on the physical layer, they are already so tightly optimized, and there are so efficient circuits available that there is just simply nothing to gain. And on top of that, we have a solid theory that by which we actually understand how these algorithms work and can prove their optimality under a wide range of circumstances. I'm aware, and the authors discuss in the paper here, this vision that of replacing the physical layer processing by a neural network. I just don't see the point. A point could be for NVIDIA to sell chips, obviously, but beyond that, there's just no technical reason to do it. There could be algorithms or niche problems where we don't have good models, dealing with certain types of mobility, maybe channel prediction to the extent it's needed, where neural networks definitely can play a role, there's no question. But replacing already well-proven and extremely optimized and energy-efficient solutions with machine learning just makes very little sense.
Right. No, I think that keeping the algorithms that we have and potentially fine-tuning them in some situation when we know that there is something to learn. I usually say that there are, if I remember, 3 different things you can learn that is really important. One is user mobility, as you were saying, that you can track them. Other things is user behavior, such as what kind of applications are they using and how do they access data and these type of things. And then the third thing might be how does the application itself behave, at what frequency is it sending data, and how much data is it sending in their packages, and all these type of things. You might be fine-tuning algorithms based on these 3 facts.
Oh, absolutely. But I think the question was whether the core processing at the physical layer would be replaced by neural networks, which, could be technologically, it's probably possible to do it, but there's just no point to do it. Yeah. But
what about this generative AI that has been very popular in the last year?
Yeah, that's a good question. I don't know if I have good intuition for that. Do you, Emil? What are the use cases where you would want generative AI? For me, it's a little hard to see that you would want generative AI anywhere on the physical layer. But I could imagine that maybe somewhere in the cloud, you might want to use models to... Or do you have a vision for how this would play out?
So first, when I heard this combination of things, it seemed really odd that you want to do anything generative in these situations. Apart from, of course, trying to compress data by somehow saying that I just show me an elephant, and it doesn't have to be any elephant, just generate that one, and you send a prompt. But then I saw an example from one of the big vendors where I think it was meant to help people who are overseeing the network operation. So there's a lot of data being collected in all of their base stations, and it's really hard to comprehend them. So then they could write prompts to an LLM that it was then helping them to summarize the data and explain things to them. And if they said, we would like to save some energy in this area here, can you please configure the base stations by turning off some carriers or things like that? Well, then they could communicate with the network using these LLM systems.
But that's a whole different thing. I mean, to me, that's not really using Gen AI on the. It's not even close to the physical layer to start with. But there would be more like a way of interacting with these huge systems, rather than editing a config file with a million different parameters to tune. You could tell the system in plain language that, hey, I want another access point configured to cover this spot here because a lot of people have problems with coverage there or something of that sort. And the LLM would translate that into exactly how these parameters should be tweaked. That makes total sense to me. If that's what's meant by Gen AI, but on the other hand, I mean, it's hard to see how that sort of Gen AI would create a higher load on the physical layer in terms of bit rates that we discussed earlier, that AI applications would be responsible for much of the new additional data traffic. But certainly using Gen AI models to interact with these big systems, I would find an interesting prospect.
Yeah, because we have this trend on trying to automate the operation on the networks more and more in order to not have manpower spent on trying to control the networks. And then you, of course, need a way of communicating with that autonomous network, and this seems to be the way. Okay, if we move on to satellites, we have been staying on the ground so far, but will satellites play an important role in 6G?
Good question. I think the author's view and analysis is that satellites definitely will play a role, but it will be very difficult to offer anything close to. I mean, it will be very difficult to offer area coverage with high bandwidths, which is kind of obvious once you start do a little bit of calculation. One thing that I found rather fascinating is that it has become fairly cheap to launch material into orbit. So apparently the cost has dropped. The cost of launching 1 kilogram of payload into orbit has dropped from $16,000 10 years ago to around $2,000 today. That's a factor 10 almost in 10 years. That's pretty impressive. And I don't know, I mean, whether we reach some sort of fundamental limit here, or whether the drop in cost could continue. I mean, is it technologically or physically possible that in 10 years into the future, that cost would have dropped to 10%? I mean, another 10 times? I have no idea. It doesn't seem to me, but I haven't thought about it at all carefully. So it's hard to tell, like, when we will, or whether we have approached the fundamental limit for the cost of launching new satellites, which to me seems to be what really constitutes the physical limit for how much area spectral efficiency that we ultimately would be able to offer.
Right.
What do you think, Emil? Yeah.
No, I'm really impressed by how quickly this thing with the low orbit satellites have been starting on, the LEO satellites and Starlink and OneWeb and the Globalstar and all this type of things. They have taken off, and there is also now a trend towards using them directly to devices. And I think there were some experiments claimed, at least by Elon Musk, that Starlink could deliver 7 megabit per second directly to some mobile phones in the US. Then that is of course more of a 3G speed, and you need to be outdoor. But it's interesting. I think it's really about how do you connect the countryside of the world. Should we do this with tall masts, or should we do it with satellites? And that is where the competition happened, because it's a way of covering big areas but not providing that much of total capacity per area unit. No, and I think typical base stations that we are deploying have a range of a few kilometers, and you have a 24-kilometer diameter of one beam that comes from a Starlink base station. So it is creating many such beams, but they are filling up one area. So you within a 24-kilometer diameter, you can only serve one device at a time using all of the spectrum, or cut the spectrum between them. So yeah, you have a capacity per beam, and you need to split it between the users, and you cannot come anywhere close to what a ground-based base station can deliver in terms of total capacity. But yeah, you can cover some parts of the world, and if you can make sure that a normal mobile phone can natively connect to the satellites as well, because you use 6G and not some other radio interface, and you use similar frequencies, so you directly have a radio that can tune to that frequency used by the satellite, well then that seems to be a great way of moving forward to provide global coverage.
Yeah, absolutely. I mean, my understanding is that the beam width is about a degree, which gives something like, as you said, 20 kilometers on the ground cell radius. And one active user within that cell would get the full bandwidth essentially, and then the satellites can form many such non-overlapping beams simultaneously. So that's what essentially dictates the area spectral efficiency. To me, this seems to be all come down to where the demand is. I mean, is it to cover the countryside in some countries, or would it rather be to cover like the oceans, or provide air traffic with broadband, and who would eventually pay, and what would be the cost, and what are the fundamental limits for how small you can make the satellites, how cheap you can make them, and how much it will cost to launch them into orbit, and how long they will last while they are in orbit, and what will happen with them after they reach their end of service the life.
Right. Yeah, and it seems like the life of service is not very long for these satellites
it seems
as well.
It's like a handful of years or something, and I suppose after that you either have to shoot them down or have them blow up or keep them in orbit. But I would increase. Eventually, you would become crowded up there, right? So you could be careful not to collide.
But from a business perspective, it seems interesting that if you would like to cover certain places in the countryside, then if no one lives there, but people are sometimes going hiking there, of course it's great to have coverage, but it might be hard to motivate putting up a mast only for that perspective. Yeah. In principle, you can build 300-meter tall masts and cover large areas in the countryside with them, but it's not happening. But since the satellites are naturally circling around the globe, then if in some parts of the trajectory there is a lot of people who could pay for that trajectory to be there, well then that might also compensate for the fact that part of the time the satellite is covering this hiking part of the world.
That's
as well.
Right. And if you go hiking, you might not need that high bandwidth anyway, probably. So.
No, exactly. All right, one more topic that I mentioned towards the end of this paper is ORAN, or Open RAN.
Yeah.
What role will it play in 6G?
Yeah, that's a good question. I think you know this best, Emil. You blogged about ORAN the other month, I remember. And now going with the view of the authors here is that ORAN is coming. It's inevitable. No, ORAN will succeed. I'm quoting from the paper. ORAN will succeed, but conditionally. Our assessment is that RAN disaggregation is inevitable, indeed already well underway, but that only a small set of trusted vendors and system integrators will ultimately succeed in the 6G ORAN economy. I mean, at the surface, ORAN makes a lot of sense, right? You would be able to build or buy components that you assemble together and that operate using an interface that's completely specified in an open standard. At the surface, that seems to be the way to go. I think the difficulty here is that it also comes with a lot of costs. It comes with costs in terms of really making sure that these components comply with a specified standard and that they operate well together. And if you think about it in telecoms, we are so used to systems that are basically 100% reliable. We don't tolerate errors. The systems have to work always, full stop. So a lot of effort will be required into testing and into making sure that, well, buying particular components and testing them together and then sticking with those combinations. So it isn't completely clear. And I think I would agree with the view of the authors here that it's not clear that the complete ORAN vision would eventually succeed, but maybe to some extent in that some well-tested combinations that operate over an openly specified interface could be deployed. Another aspect is efficiency, that if you build a proprietary system, then, well, you might use the open interface by all means, but you could also send proprietary control messages that aren't specified in the open standard and that enhance performance and improve energy efficiency. And that would just not be possible if you have to rely completely on this open interface.
Right. No, I think it is something that is certainly happening, and it challenges this traditional thing that we have only standardized the aspects that are truly needed to make interoperability between a base station and a mobile phone to work. And now we want interoperability between different pieces of the base station as well, so you can buy them from different vendors. And I think the starting point from this is that there is not that many vendors that you can buy your equipment from, and the political issues in the world might even reduce the number of choices that you can make even further. Then when you are building a network, you are making a deal with maybe one vendor today and you say, I want to buy all of this equipment, can you give me a good deal? And you can play the different big vendors against each other. Then once you have deployed the network and you're locked in to one vendor and you need to buy more equipment, you have the problem of not having much bargaining power anymore. And from that perspective, then the openness and interoperability makes sense, that you still keep this bargaining power. You can say, well, I need a new base station for this place, and if you can't give it to the same price as you offered before, I will get it from this other vendor. So ORAN could deliver these type of things, but as you were saying, these are really complicated systems, and the chance that new vendors would show up that can build things that are as highly capable as the ones that traditional vendors can already produce is not that big. But if it happens, then it's good for the mobile operators.
Yeah, absolutely. I mean, but this whole thing with ORAN seems to be politically, from an industry politics perspective, rather sensitive. So I remember once that I was invited to give a talk at the workshop, and they told me that you can talk about anything you like, but please do not talk about ORAN, which I had not planned, by the way. But it seems to me again that there's a lot of tension here between those who want it and those who don't want it, and it's difficult to decode the exact motives for the different standpoints among different stakeholders.
But I think what really happens in the network now is the virtualization of different network functions, so you can run them on general purpose hardware, and you can collect them in edge clouds instead of having dedicated hardware to do them at the base station sites. And there's also this AI maybe powered automation of the network operations, and I think this is something that the operators really benefits from in terms of lowering cost in the operation part. And then the O-RAN Alliance, who is behind this O-RAN standardization, they are piggybacking on that one and say, if you follow our specifications, you also get openness and interoperability, so why shouldn't you get that? So my impression is that now when there are some big operators that are investing in O-RAN compliant hardware, they are really after the virtualization and automation aspects, and the fact that they get some interoperability benefits in addition. It might be useful in the long run, so why say no to that option if it gives you some more bargaining power in the long run? So now we have come to the end of the paper. Is there anything you think were missing?
I think two perspectives that are missing. One is the role of distributed MIMO, and it might be debatable to what extent this will actually be deployed in the time horizon envisioned for 6G standardization. But one more time, in my view, distributed or cell-free massive MIMO is really the ultimate physical layer solution for providing high area spectral efficiency and uniform quality of service. The second thing I would have liked to see a discussion of is network controlled repeaters as a way of enhancing coverage, basically doing the job of a REIS, but without the complexity and the bulkiness of a REIS. Maybe that's something we should return to, Emil, at some future point in time.
Yeah, I think so, because distributed or self-free MIMO and RIS for that matter are things we have covered in previous episodes, so one can go back and listen to those ones as well. But network control repeaters is not such a topic, so let's come back to that in a future episode.
Absolutely.
All right, so great to talk to you today, and we will keep in touch and talk more in the next episode.
Absolutely, Emil.
And thank you
Bye-bye.
to everyone for listening.